Happy day and welcome everyone. So what I'm going to do before we actually do the lab is I want to give you a little bit of a general idea of what's going to be happening and some of the important information that you need to know prior to doing the lab, as well as some of the information post-lab that we also need to talk about. And so what we'll do is we'll talk about it here first, and then we'll head over into the lab to actually perform the experiments. Okay, so the first thing is, what's the problem? So I'm just going to read this part here to you, and then you can kind of highlight some of the other areas. So you're working for a chemical company. Your team is tasked with trying to figure out the delta HF for ammonium nitrate, NH4NO3. Other chemists in your lab have already done some calorimetry work to find some of the delta H values for some helpful reactions that can help you attain your goal. So you're all kind of working in this for this chemical company together. You will need to perform a couple of calorimetry experiments to help fill in some blanks to be able to get your heat of formation of ammonium nitrate. So that's going to be your target. So you can see written right here is our target equation. So it's this N2 plus 2H2 yields 3 halves O2 to give us NH4NO3 solid. This is very important. Notice when we say the delta HF, the heat of formation, it is forming the substance, 1 mole of it, from its elements in their standard state. So you can see, if I were to look on the thermo chart, nitrogen would have a value of 0. So would hydrogen, and so would oxygen. Now, I'm going to tell you right from the start, you could go to the thermo chart, and we could arrow over into the nitrogen section where ammonium nitrate is, and bam, there it is right there. Now, you're not going to get the exact number because we're doing this experimentally, okay? And none of the numbers that are actually given to you that the chemists even figured out are going to be exactly perfect, okay? But it's going to give you a nice idea of how these experiments will work. So just to kind of give you an idea of that and a nice go-to to try to figure out if you were close, if your value was close. So again, what we're trying to figure out is what is the heat of formation of ammonium nitrate. Okay, so let me give you a little bit of background here too. This lab typically would be, if you were in class, would typically be a 3-part lab where some groups are going to figure out ammonium nitrate, some groups will figure out ammonium chloride, and then other groups will figure out ammonium sulfate. So just to simplify it again, we're going to end up just doing ammonium nitrate for this experiment. Okay. So there's a little bit on Hess's law, and then it talks about Hess's law of manipulation. Okay, now, we know that you can do products minus reactants to be able to figure out what the delta H is for a reaction. And typically, the way that a reaction is written and balanced is using whole numbers as the coefficients. So, for example, this top reaction probably did not look like that. What it probably looked like was it probably said 1N2 plus 3 H2s yields 2 NH3s. And so the delta H value in that case was probably double this. So it was probably a negative 91.6 instead. Well, so what we needed to do to make this match this NH3 was use our circle, squares, and triangles. And so I could use a circle here and say, okay, well, based on my target, it's on the same side, but, so the side is correct, but I know that I need to divide everything by 2. And so what I would do is I would divide all of it by 2, including that negative 91.6 to get the negative 45.8. Okay, so again, you could be given these intermediate reactions in a whole bunch of different ways. You just need to make sure that once you manipulate and you check 2 things, you check the side it's on and you check the coefficient, then it'll match your target. Once you get those 2 numbers, all you do is you add these 2 up, and so that's how they get this negative 81.2 answer. Okay, so that's just an example of how Hess's law, as simple as it can be, how Hess's law works. Okay, so then let's continue on here. All right. So what you figure out working for this company is that these 2 missing puzzle pieces in figuring out the delta HF for ammonium nitrate are 2 steps. So if you can get the neutralization reaction for, in our case, X is going to be nitrate, so it's going to be NH4NO3, same thing here, it's going to be NH4NO3, and same thing on these, so your X is your nitrate. Then we needed to figure out what the neutralization delta H was for neutralization and delta H for dissolution, which is why this is actually going to be a two-part experiment. Okay, so it explains that what you're really recording is the temperature change of your reaction, so whether the temperature rises or falls, so you're looking for delta T, but of course, when you're using a calorimeter, you need to make sure that you know what the mass is inside of the calorimeter as well. And so there are a whole bunch of different things that we need to make sure of when we do this lab. All right, so here are some side notes and disclaimers, okay, because I'm kind of minimizing this quite a bit here. So the first thing is NH4OH is actually, so ammonium hydroxide is actually ammonia plus water, okay? So it's ammonia dissolved in water, and ammonia, NH3, in its natural state is actually a gas. So it's not going to be aqueous, and the solutions that we're using are aqueous. But I want you to know that when we buy the solutions, it typically says that we're buying ammonia, even though it's ammonium hydroxide solution, okay? And it usually comes as a highly concentrated solution, around 18 molar, and so I dilute it down based on what our needs are. And you're gonna see in this experiment, we needed a 1.5 molar solution. Okay, so that's just a little bit of a disclaimer about the fact that even though we're writing NH3, we're using NH4OH, okay? Second thing. So this is a part that I'm excluding or just kind of using as like a disclaimer in this lab, where normally if you were in class, we would use this part. So when you use the calorimeter, you first want to make sure that you start off with one of the reactants coming to a constant value inside of your calorimeter, okay? Now, you're thinking, okay, but it's been sitting at room temperature, so isn't it at a constant value already? Oh, the only thing is that once you put it inside of this calorimeter, the temperature is going to change a little bit because of the metal piece and the styrofoam that's in there. So just keeping that in mind, not going to change much, but what you want is you want a stable temperature before you start. And so they ask you to graph this, and here's why. So in the beginning, we can see that our temperature is remaining constant, and so this is before reacting. So for our reaction, we will put ammonia inside of there, and we're trying to neutralize it. So ammonia is a weak base. It's ammonium hydroxide again. So that's our weak base. And so we let that sit, and then we end up adding, in our case, it would be nitric acid. So that's the neutralization part. The HNO3 is going to be added. So that's what they're calling time zero, all right? And what you're supposed to do is, it looks like every 15 seconds, they are recording what the temperature is, all right? They're recording the temperature. So they record it, record it, record it. Well, what they say is, even though the highest temperature it looks like they're getting is something around this value right here. Let's see, let's backtrack this just a touch. So it looks like it's this value right around here. But because there is loss of heat to the calorimeter, to the parts of the calorimeter, if you extrapolate and you come back, you draw a straight line from where it starts decreasing here. So once it reaches its max, you keep on recording after that. And if you do that, then what you should see is you want to get your temperature at time zero. And so you kind of extrapolate back and you figure out what time zero would have been, and that's how to correctly do it, okay? So we're going to skip that because it doesn't make a huge difference. You'll see it doesn't really make that big of a difference in the experiment, especially because we really want to just make sure that we're getting the idea here. If you were working for a company, then that would probably be an important piece. But for our uses now, we're going to ignore that part. Okay, so normally you would be doing the graph and things like that, but we're not going to. So it says in red, it doesn't change the results drastically, so we're going to refer to this as one of our sources of error. There was heat loss due to the calorimeter walls and leaks in the calorimeter. Okay, all right, this part is really important and you need to remember this. Okay, this is data from other teams in the company. So now it says, surprise, these values are very close to the thermo chart. So let's take a look, for example, I don't know, let's take a look at team B that used hydrochloric acid. Okay, so let's go to the thermo chart and let's find our chlorine section where hydrochloric acid is. Okay, here it is. And so it says that it's a value of the heat of formation, again, that is making it from its elements in their standard states is negative 167.2. And these are elements in their standard states, which means these both have zeros in value of kilojoules per mole, but we see it's negative 165.1. It's really close, okay? So I'm saying that it's experimental. It says you will only need the data from teams A and C to help solve your problem. The others would have been helpful if we were doing the full lab where different groups had different salts, okay? But since we are only doing this for the nitrate, then we need team A. So you're going to want to make sure that you mark this somewhere, that you remember this. We're going to need team A, and we are going to need team C. So the only two that we actually need are ammonia, because we're using ammonium nitrate, and then we need the nitric acid one because that's what we're using in our lab. We're not using hydrochloric or sulfuric acid in ours, okay? So just to give you an idea of that as well. All right, the procedure. Now, you are in your pre-lab going to take this, and I'm going to show you in just a second here, and you're going to make a recipe-like procedure for this, okay? But it's going to be minimized and abbreviated, so I'll show you that after. First is just your apparatus. It is just this simple calorimeter with a thermometer, and we've got the neutralization part, and explains what to do. Again, we are not going to be recording, even though you're going to write this as if you did in your procedure. We're not going to be recording the temperature every 15 seconds. All we're going to do is we're going to get that max temperature change, okay? So it's either going to be a min or it's going to be a max, depending on whether the temperature is rising or falling, if it's exothermic or endothermic, okay? And part one is neutralization, which means we're adding an acid and base to make water and salt, but in this case, you're going to see, because it's ammonia, the equation works out a little bit differently, all right? The second part is dissolution. And dissolution is exactly what it sounds like. We are going to be dissolving. Well, what are we dissolving? We have three choices of salts. Of course, again, the only one that we're going to be doing this for is ammonium nitrate. Okay, so don't worry about the other ones. And there's the procedure again, and it explains what to do. You don't have to worry about the sulfate. So it says adjust relative volumes for sulfate. We're not worrying about that. Okay, so that's the procedure. All right, so here comes the lab report piece. Okay. So I've minimized this, completely minimized this, just so you know. It's going to be a lot easier than what has been done in the past. But it's really nice to make sure that you have a good idea of what's happening, that you've got some vocab down, and it's going to help you when it comes time for your evaluations. So the first part is the introduction. So it says in paragraph form, answer the following. What is the purpose? Define enthalpy of formation. Explain what neutralization is. What are you neutralizing? It's good to have chemical reactions, so go back to that first page. And by the way, I'm going to mention this a couple of times, but you can just copy and paste. So the reason why I'm sending you a Google Doc copy of this is so that you are going to make your own Google Doc. You are not going to have any of the information from the prior pages. The only thing that you're going to need is your report, okay, is your one sheet that you're turning in. So in paragraph form, you're going to explain this. So what I was saying is you can copy and paste reactions and things like that. That would be helpful, okay. So what does it mean for a reaction to be exo and endo? What are the signs? What is Hess's law? What is it and how do we use it? Okay, so the procedure. I started a sample, and again, you can just copy and paste this part and then continue on if you want. So I'm allowing you to use this part because we're kind of doing this together. So if you go back to the procedure, number one, yes, it's like a full paragraph, but I just said set up the calorimeter. I mean, as easy as that, right? So set up your double wall calorimeter. Part one is neutralization. So it says here that you are going to measure 25 mils of the 1.5 molar and transfer it into the calorimeter, and then prepare 25 mils of blah, blah, blah. So what I did was I said, measure and place 25 mils of NH3 in calorimeter. It can be abbreviated, it doesn't have to be complete sentences. 3, in grad cylinder, pour 25 mils of 1.5 molar HNO3. Yours is HNO3 because your salt is NH4NO3, so just to remember that. And you might want to make note, because it does make note here that we're not actually mixing it yet. So it does say, that you're prior to mixing, you're not doing any of this yet. So just keeping that in mind, okay? And then keep going through part two. So you're going to keep your procedure going. Materials, you can just literally copy and paste that calorimeter picture. The only other materials you need to Google are a balance, a spatula, and a 25 ml cylinder. That's it. And then your data and calculations. So we're going to do one of the calculations together right now. It's the pre-lab calculation. Okay. So it says, calculate the grams of solid to be dissolved in part 2. Of the 3 salts, again, we're only going to be using NH4NO3. That's to be added to 50 mils to get the same concentration as part 1. So I know I'm looking for grams of the NH4NO3, grams of NH4NO3. Okay, and let's circle that. And then we can start, if I'm ending with 1 unit, I want to start with 1 unit. Don't forget, you're always going to keep remembering that. So this really should say 50.0 milliliters. That's going to be our volume of the solution. Okay, so I'm going to switch that right away and 3 loops back, 1, 2, 3. So I'm going to get 0.0500. Let's make it 50.0 liters of the solution. Okay, so 0.0500 liters of the solution is what I'm trying to get. And now I have liters. Okay, well, from liters, if you remember when we did this in the second unit, we could use moles per liter. So we're trying to get grams. So we know the molarity. We said that we want the molarity to be a 1.50 molar. So let's make this 1.50 moles per liter of the solution. Now I'm in moles, awesome, because all I need to do now is switch to grams. So I can just look it up online, Google it, the molar mass of ammonium nitrate, and it ends up being 80.04 grams per mole. So now I'm all set because my liters cancel out, my moles cancel out, I am left with grams, and I multiply this and I get 6.00 grams of NH4NO3 in order to make, again, I want to make sure you understand what we just figured out, in order to make a 50 milliliter solution of the 1.5 molar. Okay, so that's what we were trying to do. So that's number 1. All right, so you can just copy. Again, you'll want to type this. You can use tables if you want. That's the easiest thing to do. All right, and get used to it, please. All right. So now what we're going to do is we'll fill in the lab data, and then let's take a look at the post-lab calculations because this is really important to be able to get down. First, they're giving us a specific heat. There's a big tip, big, huge tip. So what you want to do is you're trying to experimentally show the experimental data for delta H of both reactions, okay? The neutralization and the dissolution reaction. Well, fine, delta H equals MCAT is what we're going to use. We know that. The only thing is MCAT only gives you kilojoules. It only gives you kilojoules. So put your arms out. Kilojoules, moles, kilojoules over mole. Okay, so keep that in mind that anytime you want kilojoules per mole, you can use delta H equals MCAT to find your kilojoules, but then you have to divide by your moles. And the moles are specifically either 2 ways that we're going to do this, either molarity times volume, that will give you moles, or if you know what the substance is, you can simply switch grams to moles. If you're using the molecular weight, if you know the mass of it, you can do grams to moles. But if it's a solution, and you're going to need both ways, by the way, okay? If it's a solution, molarity times volume is what is going to give you moles. So keep that in mind. And then also, don't forget to include the sign for delta H. And my recommendation is to always do that after. So you just think, did my temperature go up or did my temperature go down? M should not have a sign. C should not have a sign. Delta T should not have a sign. The only thing that carries a sign is delta H. Otherwise, it's incorrect, okay? You'll lose points on putting signs in for other things. Okay, then what you're going to do, the very last part is, you're going to use Hess's law, the reactions above, so your answers to these 2 right here, as well as the answers from teams A through D on the bottom of page 2, and you're going to try to figure out what your target delta H value is. Don't forget, the target is under your sum line, okay? So the target is under your sum line. We know what we were looking for back from the very first page was the heat of formation of ammonium nitrate. That's what our final target is. So you're going to end up using those reactions, and it ends up being 4 reactions. So I'm kind of giving you some big tips here, but it ends up being 4 reactions that you're going to use and you're going to manipulate. You may not need to change some of them, okay? And I'm going to kind of tell you, most of them you won't need to change. But if you do, and you check to see and you're like, wait a minute, that one should be times 2, or that one should be divided by 2, or that one needs to be flipped and reversed. So make sure that you show all of that. And so you must show the four equations that you use to get your final target. You have to show how you added them up. And so you can use the strike through like I did here. And then again, another tip, like I said before, you can copy and paste reactions rather than retyping them. And you need to tell what you did to each reaction for your manipulation. So again, if you reversed it, if you divided by 2, if you multiplied by 2, just make sure that you let me know, okay? Brief conclusion here. Why was this called the enthalpy of formation lab? Was the neutralization reaction exothermic or endothermic? How do you know? And then what about your dissolution reaction? It could be positive or negative on that one. So how do you know if it's positive or negative? How is Hess's law helpful in solving your problem? And then list 2 errors in the experiment. All right. Okay, so that's kind of our lowdown as to what you're doing for this lab here. Happy day.